Morning. So today we will attempt a tutorial on Kaplan Turbine. We will solve 2-3 numerical problem based on Kaplan Turbine. So the first problem, a Kaplan turbine has the following specifications: rated discharge 260 meter cube per second, head 10 meter, speed 80 rpm, runner hub diameter 2.3 meter, runner vane tip diameter 6.7 meter, power produced 18,000 kilowatt, hydraulic efficiency 85%, find the ratio, speed ratio, overall efficiency and specific speed. So here you have to determine the flow ratio, speed ratio, overall efficiency and specific speed of the turbine. So first of all, let us list the given data. So you have given discharge 260 meter cube per second, then head 10 meter, speed 80 rpm, then runner hub diameter, which is dB, is 2.3 meter. Runner tip diameter, that is our outer diameter DO, 6.7 meter. Shaft power is 18,000 kilowatt. Then hydraulic efficiency 85%. So these are the data given to you, and we have to find flow ratio. So KF, speed ratio, overall efficiency and specific speed. So these four parameters have to be determined. Now let us first of all find out the overall efficiency. We have the equation for overall efficiency. Eta not equal to shaft power by water power. So water power is WUH. So we have given the head, power, discharge, and we know the value of specific weight of water. So let us substitute the known quantity here. So it is 18,000. So 18,000 kilowatts. So into 10 raised to 3 divided by specific weight W is 9810 Newton per meter cube. So 9810 into discharge is 260 meter per second. That into head is 10 meter. So the overall efficiency you calculate, when you calculate, you get it as equal to 70.6%. So this is the overall efficiency of the given Kaplan turbine. Now let us find the flow ratio. In order to find the flow ratio, let us first of all find out the flow velocity that you can obtain from the discharge. So the discharge of the turbine you can write as area of flow multiplied by flow velocity. So that is discharge is Q equal to this area is pi by 4 d naught square outer diameter square minus hub diameter. So this into Vf. So we have given the diameters, both d naught and db are given in the question. So let us substitute. So it is 260 meter cube per second, that is equal to pi by 4 into what is dB? dB is 6.7. So it is 6.7 square minus 2.3. D naught is 6.7 and dB is 2.3 into Vf. So you can obtain the flow velocity Vf from there. So the flow velocity Vf equal to 260 by this area pi by 4 into 6.7 square minus 2.3 square. So this velocity you will get as 8.36 meter per second. So the flow velocity we got as 8.36 meter per second. Now from the flow velocity you can find flow coefficient. How? We have this flow velocity in terms of this head of the turbine, that is flow coefficient into root of GH. So this Vf is 8.36 equal to Kf into root of 2 into 9.81 into 10. So you can solve that equation to get the speed ratio, and after solving you get Kf as equal to 0.597. So that is your flow coefficient. Now again you can find out the peripheral speed of the rotor, u as equal to pi dn by 60. Pi dn means here d has to be outer diameter df, and this is also equal to speed ratio into root of gh. So this pi d naught you can d naught as 6.7 into rpm. Rpm is 80 rpm, so 80 by 60. So this will be equal to ks into root of 2 into 9.81 into h is 10. So that gives you the speed ratio value. So the speed ratio of the turbine is, after solving, you get as equal to 2. So this is the speed ratio of the turbine. Now the specific speed, the third parameter, specific speed of the turbine is, we have this equation n root p by s raised to 4. So all the data are known. So let us substitute this. N has to be substituted in RPM into root of power should be in kilowatt. So 18,000 you have to substitute. No need to multiply it by 10 raised to 3. It has to be in kilowatt divided by 10 to the power 5 by 4. So the speed, so the specific speed we get equal to 6.3. This is the specific speed of the turbine. So when you write the specific speed, you need not write the RPM. Even if you write RPM, that is not a mistake. That is not wrong. So you can write this RPM. Even if you don't write RPM, that doesn't matter. So we have now obtained all the unknown parameter that are asked to solve. So this is flow ratio. We have solved overall efficiency. You got so this is the first thing that is asked to determine overall efficiency. Then speed ratio, not speed ratio, flow ratio, flow ratio. So flow ratio got the second parameter, flow ratio. Then speed ratio, yes, this is speed ratio. And the fourth one is speed. So that completes the problem. And let us move on to the next numerical problem. So the second problem, the hub diameter of a Kaplan turbine working under a head of 20 meter develops 11,000 kilowatt shaft power. The outer diameter of the runner 3.5 meter, the hub diameter 1.75 meter, the guide blade angle at the extreme edge of the runner 35 degree, hydraulic efficiency 88%, overall efficiency 80%. Determine runner angle at inlet and outlet and the speed of the turbine. So this is the velocity diagram for the Kaplan turbine. And if the flow is axial, the exit velocity diagram is a right angle triangle. So we have VW2, that is the world velocity at exit is 0. So let us first of all write down the given data. So we have given the head of the turbine as 20 meter. So H is 20 meter. Turbine developed 11,000 kilowatt is the shaft power. Then the runner diameter, outer diameter of the runner is 3.5 meter. Then diameter of the hub for both is 1.75 meter. Then the guide blade angle at extreme edge of the runner. That means at the inlet, the guide vane angle, which is alpha. So alpha is 35 degree. Then hydraulic efficiency, eta H 88%. Overall efficiency 80%. So these are the known data in the problem, and they are asked to determine the vane angles at inlet and exit, that is theta and phi. So the inlet it is theta, exit it is phi, two angles. Then speed of the turbine is Pm. So these are the unknown data to be determined in the given problem. So to solve the problem, let us start from the equation of the overall efficiency. We have overall efficiency theta naught as shaft power divided by runner power. So this equation you are given eta naught is known, P is known, H is known. So you can calculate the discharge of the turbine. So discharge Q will be P by eta naught W into H. So let us now substitute P 11,000, 11,000 raised to 3 divided by eta naught is 80%, so it is 0.8 into W specific weight of water is 9810. So that also you can note down W is 9810 Newton per meter cube. So it into H, head of the turbine is 20 meter. So this gives you the discharge of the turbine. The discharge after solving, you get it as Q equal to 70.1 meter cube per second. So this is the discharge requirement of the Kaplan turbine. Now from the discharge you can solve the flow velocity at inlet. So this discharge Q equal to the Kaplan turbine. Kaplan turbine. The discharge equation is flow area. Flow area here it is pi by 4 into d naught square minus dB square is into Vf1. So Vf1 is Q divided by pi by 4 d naught square minus dB square, so that we can substitute here. So this is equal to discharge is 70.1 divided by pi by 4 into 3.5 square minus 1.75 square. That is the area. So after calculating, you will get this as 9.7 meter per second. So this is the flow velocity at inlet of the turbine. Now from the inlet velocity diagram, you can get the other velocity values using this non-data. Non-data means Vf1 now you obtained as 9.7, then this alpha is also there. So now let us find the world velocity Vw1 that you can determine by taking the tan of the alpha. So you can write tan alpha, that will be Vf1 by Vw1. So from the inlet velocity diagram, so from the inlet velocity diagram, we have tan alpha equal to Vf1 by Vw1. So this Vw1 will be Vf1 by tan alpha. So Vf1 is 9.7 by tan of 35. So you can calculate the world velocity Vw1 and you will get it as 13.87. After calculating, you get it as 13.87 meter per second. Now to get the value of the blade speed, peripheral speed of the rotor at inlet, we will use the given hydraulic efficiency. So for Kaplan turbine, hydraulic efficiency eta x is VW1 U1 by G into H. You know VW2 is 0. So hydraulic efficiency will be VW1 U1 by GH. So here the only unknown is U1 that you can solve. So the hydraulic efficiency is 0.88. It will be equal to 13.87 into U1 by 9.81 into H is 20 meter. So from after solving, you get the speed, peripheral speed of the rotor at inlet as 12.44 meter per second. So it is 12.44 meter per second. Now this value you can use to get vane angle at the inlet. Now again, if you go to the velocity diagram, you can write here tan theta is equal to Vf1 by Vw1 minus U1. So now tan theta equal to, again from the inlet diagram, tan theta equal to Vf1 divided by Vw1 minus U1. So this is equal to 9.7 divided by 13.87 minus 12.4. So that gives you the theta value. So after solving, you will get theta, that is vane angle at, so this is runner vane angle at inlet, theta equal to, you get 81.6. Now let us get the value of the vane angle at exit from the exit velocity triangle. So in the exit velocity triangle, exit velocity diagram, we can have U1, U2 as equal to U1 because it's axial flow turbine. So U2 equal to U1, which is again 12.44 meter per second. Axial, it is axial flow. Axial flow. Only in radial flow, U1 and U2 differ. So in axial flow, it is U2, U1. Kaplan turbine is an axial flow, so U2 and U1 are equal, 12.44 meter per second. Again, the flow velocity is Vf1, Vf2. At exit, that is same as Vf1. There is no change in flow velocity, which is again 9.7 meter per second. So this value, you can, values of the U2 and Vf2, you can use to get the value of the runner vane angle at the exit. How? You take tan phi, see from the exit velocity triangle, tan of that angle, you can see the diagram. Here it is, tan phi will be Vf2 by U2. So from the exit velocity triangle, tan phi equal to Vf2 by U2, which is 9.7 by 12.44. So this is the runner vane angle at outlet or exit, phi equal to, we get it as 40.3. Now speed of the turbine you can calculate from the known speed of the rotor. So U1 is also equal to pi d naught n by 60. That means 12.44 equal to 5 into 3.5 into n by 60. So you get speed of the turbine n as equal to 68 rpm. So we have obtained all the unknown parameters that are asked in the problem. Okay. So the next problem, the third problem, a Kaplan turbine runner is to be designed to develop 9,100 kilowatt. The net available head is 5.6 meter. The speed ratio 2.09, flow ratio 0.68, overall efficiency 86%. The diameter of the bose is one third the diameter of the runner. Find the diameter of the runner, its speed, and specific speed turbine. So in this problem, the given data they are given the shaft power which is 9,100 kilowatt, turbine head 5.6 meter, speed ratio Ks 2.09, flow ratio 0.68, overall efficiency of the turbine is 86%. And we have given the relation between the runner outer diameter and the hub diameter. That is 1 by 3. So dB equal to 1 by 3 of dO. So these are the known data in the question. And we are asked to find D naught runner outer diameter, speed, and specific. So now let us start from the given values of the coefficients, speed ratio and flow ratio. We can calculate the speed of the rotor as well as the flow velocity. So the speed of the rotor U1 or U2 is Kf root 2gh. So U1 equal to not Kf, sorry, it is Ks speed ratio. So it is 0.68, sorry, 2.09 into root of 2 into 9.8 into 5.6. So you get the speed as 21.95 meters per second. This is 21.95 meter per second. Similarly, the flow velocity is flow coefficient into root of 2gh. So this is equal to 0.68 multiplied by 2 into 9.81 into 5.6. So after calculating, you get this as 7.12 meters. So now you obtain both the speed of the rotor and the flow velocity. Now let us find the discharge of the turbine. So to find the discharge, we have given the overall efficiency of the turbine as 86%. So now we will define the overall efficiency eta naught as equal to E by water power, which is WQH. So in this equation, except the discharge, all other values are known. So the discharge of the turbine is equal to E by eta naught W into H. So if you substitute here, is 9100 into 10 to the power 3 divided by eta naught 0.86 9810, which is specific weight of the water, into head 5.6. So after calculating, you get the discharge through the Kaplan turbine as 192.5 meter cube per second. So this is the discharge through the turbine. Now from the non-discharge value, we can calculate the runner diameter. So let us write the equation for discharge. Discharge Q is also equal to the flow area, which is pi by 4 into d naught square minus dB square into Vf, flow velocity, Vf1, flow velocity at the inlet. So the discharge, now let us substitute the discharge value just now we calculated. So it is 192.5 equal to pi by 4 into this is d naught square minus dB, we have given it is 1/3 of the outer diameter. So d naught by 3 square this into Vf1. Vf1 we got as 7.12. So 7.12. So that gives you the value of the outer diameter. After solving, you get the DO value, outer diameter of the runner, as 6.21 meter per second. We solve, get the naught as equal to 6.21. Now to find the speed of the rotor, you write the equation of the speed in terms of the diameter and speed. Diameter and, so that is so the speed of the rotor U1 as pi d naught n by 60. The speed n is 60. 60 U1 by pi d naught. So it is 60 into 21.95 by pi into 6.21. So you, after calculating, you get this as 67.5 RPM. Now specific speed of the turbine is again the same equation what we have written in the previous problem. So N root P by x raised to 5 by 4. You substitute it as Ns equal to N 67.5. Always remember to substitute this N in RPM, then power in kilowatt. So in this equation you need not convert the power into watt. You put the power value in kilowatt divided by head, it is 5.6 to the power 5 by 4. So the specific speed value you get as 746. Okay, so that completes the third problem that you can end the tutorial on Kaplan Turbine. Okay, thank you very much.